morning. This is a third lecture. The last lecture, I couldn't finish M convexity, so just let me finish it very quickly. The main topic here is separation theorem. Okay. So this was remaining. Or actually, for the problem session today, I'm in charge. So part of this theorem should be our exercise for that. So we were talking about M-convex functions, okay? And theorem for local equal global is the following. So F is M-convex, and X is just a point where the value is finite. And then the theorem said that X is global minimum if and only if it is locally minimum in the following sense. So we compare X with some neighbors. And neighbors is this form. Decrease one component by 1, increase another component by 1. And if this is true for any ij, of course this direction is obvious, but the other one, the converse, is also true. And this is really an easy exercise. So the first problem would be this for tomorrow, for today's problem session. And second, this is important, is convex function extension. The statement is simple. The theorem says, I'll say convex. So remember that we had 5 important properties for discrete convex function that I featured at the beginning. So this corresponds to that. Okay? And say F is M-convex function. So assume this. Then F is convex extensible. So this is a statement that we naturally expect, but we have to prove it because definition of M convexity refers only to integer points. Okay? So let me do it very quickly. But if you remember the proof for L-convex function, we had a constructive method based on Lovász extension. Okay? But here, we do not have such an easy construction. We have a proof, but we don't know how to find this convex extension. Okay? The proof goes as follows. Okay? We use this characterization. F convex extensible if and only if. So for any slope, so maybe it's better to draw a picture. It's a very simple picture. In one-dimensional case, the function may look like this. This is not convex extensible. Okay? So to detect such point, we consider such a slope and look at where the slope touches the graph. Okay, so for each p, the slope, define bp to be the minimizers of function fx and subtract linear function defined on P. So this corresponds to slope. Then these points are the minimizers. And if this doesn't have such a hole, so in this case we have some hole here. Okay, if this is convex in this sense, okay, take the convex hole, then it will include this point. Then if you take the intersection, then it is this left-hand side includes this, but this is forbidden. Okay, so this is a characterization for convex extensibility. And we want to prove this for M-convex function. Okay, so then this set BP has a characteristic property. So what's the property of BP? First, fx is M-convex, so adding or subtracting linear term doesn't change M-convexity. The entire thing is f minus p is M-convex, so it satisfies the exchange axiom. Okay, so so let's call it fp. This is called fp. So we have such an exchange axiom for fp. Okay. Okay. So for any I such that xi is bigger than yi, then there exists some j. So basically we have this type of inequality. But now x and y, suppose x and y belongs to BP. This is the minimizer of this function. Then x and y are minimizers, so these two must be minimizers. So BP has the property that for any x and y and any I such that xi is larger than yi, there exists some j such that xj is smaller than yj, and we have exchange. This is in BP, and y actually this is what we have seen. Okay? In the special case, this is a simultaneous exchange axiom for matroid basis. Okay? But here we have integer points, not 0, 1 point, but still we have this property. Then we can argue by simple argument that this property implies this. Okay? This is also a good exercise. Actually, I could not find explicit proof of this statement because usually people define the convex part first, okay, using some modular function. Then this is obvious. Okay, so this is a proof for convex extensibility. But we will use this in the proof of separation theorem. It is clear to you? Or maybe some notation? Or so such a set satisfying this exchange axiom we call M-convex set rather than function. Okay? Actually, this is the same as integer point of integral base polytope. So this is the ordinary terminology. But here I'd like to emphasize the symmetry between M and L, so that I'm using this terminology. Okay? But mathematical object is already known, very well known in combinatorial optimization. Now, I go on to the main section. It says conjugacy, and duality. So conjugacy I explained in the first lecture for the univariate function. So it was f of this was supremum of p x minus f of x, and x was integral at that time for univariate function. So here we have n here, okay, and also the product is changed to inner product. Okay, so this is a definition of conjugate function, Legendre function, Legendre conjugate. And now, so as you see easily, if f is integer valued function, then this part is integer if p is integral. So this function is also this type. Okay? But on the condition, the very, say, trivial assumption is that f should not be identical to plus infinity. Then this would be minus infinity. So we'd like to avoid it. But otherwise, this is true. So at the beginning, I drew such a picture. Okay? But now I consider discrete function taking integer values. So in the first lecture, this was the second lecture, the real. Here, I consider integers. So then we have subclasses like this. This is L natural, this is M natural, and L is here, and M is here, and this is separable. This is separable convex. Okay. And essentially, L and L natural are equivalent, although they have such inclusion when we fix the number of variables. Okay. And all of them are convex extensible here. Extensible. So this was a picture. But now I'm claiming that these circles have a correspondence. So this is a conjugacy theorem. The theorem says the following. A theorem, conjugacy theorem, or I would say dual object. I emphasize that this is a dual kind of function associated with the original one. And the theorem says that L natural convex and M natural convex are one-to-one correspondence using this transformation. So that means that if we start from L natural convex function somewhere here, and we apply this transformation, then we go to the other side. And if you apply again, it's important to come back to the original function, okay, your starting point. And also this is the case for L and M. So as a special case, I already mentioned that for matroid, so this part, L part, corresponds to rank function. And this part corresponds to the family of bases here or independent sets. So we already have such a phenomena in matroid theory and also in polymatroid theory. But there, this is always set function, and this part is always set. So the relation is not that symmetric. But by extending to this picture, then everything looks symmetric. So today I do not prove this, but I'd like to emphasize that this is one of the important theorems in discrete convex analysis. Now, the duality. So this is conjugacy. So 3-1 conjugacy. The duality. But for separation. Okay, so maybe some of you have heard of discrete separation theorem for submodular functions of Hausdorff. Is there anyone? Well, it's good that I can tell you later. Okay, so I have. Oh yeah, we can find some modular function. That is a fundamental theorem. Supermodular. Yeah. So first, I will present a generic form of discrete separation theorem. So this is the statement that we'd like to have. Okay. So discrete separation theorem is says something like this. So f is as a discrete function. Okay? And it should be convex in some sense, which is not specified here yet. And G is concave. So underbar means takes minus infinity possibly, but it's not important. So the picture is something like this and this again. And assumption is that fx is pointwise greater than or equal to g. But pointwise means that we only look at integer points. Okay? So although I have drawn such a picture, we only have discrete points on it. And what we want is this. This is defined by alpha and some vector. Okay? So this is assumption, but technical minor assumption is domain F and domain G intersection. So this is kind of feasibility assumption, like in linear programming. So today you don't have to really worry about this. So then the statement the system consists of two parts. The first is, or I would call our separation, means that there exists real number alpha and real vector p such that if the affine function defined by alpha and p is in between, so sandwich theorem. But now x is on the integers. Okay? The statement itself doesn't refer to any convexity, just quoted convexity. Okay? And integral separation statement should be more interesting from combinatorial point of view. So if f, g both integer valued, okay? So instead of this, we have z here. Then we can take integer alpha and integer p such that this is true. Okay, this is the statement, generic statement of discrete separation. And in the next two examples, I will show that this is not easy to get. I will show a very simple example for which this fails. Okay. So the first example is very small, actually. Well, so example 1 is the following: n equals 2. And consider a function defined on unit cube, that means square, 0, 0, 1, 0, 0, 1. And I will specify function value in a simple way. Let's say f is equal to 1 here, 2, 3, 4. This is my f. And we'd like to have another function g that is dominated pointwise by this function. And the easy choice is to take the same value. Okay? So g equals 1, 2, 3, 4. So first, if this function can be extendable to convex function, so can you find a convex extension of this function in real variables? Should be easy. So we must have convexity here. So if you can imagine the picture, this is very high. So we have this folding. So this is convex in a sense, okay? In the sense that of convex extensibility, this is convex function. And here, is this concave? It is concave if we fold in this way. Okay? So this is convex extensible, this is concave extensible. And do we have separation? So real separation possible? Yeah, actually. So there is no upper P in real space. So this already shows that discrete separation, even for the real case, is non-trivial if we do have such theorem. So far we don't have anything, but if we can find a theorem, that theorem should not be very easy. And the second example, okay. Example 2, again n equals 2, and we have the same picture. Oh, no, not really the same. It's better to give the formula. Okay. So let f to be given by maximum of 0 x1 plus x2. So x1, x both integers. So by this formula, it's obvious this can be extended to a convex function and takes integer values. So now I'm considering the integral separation. So this is integer valued convex extensible function. And g to be minimum of x1 and x2. This is again integer valued. But here we have minimum, so that is why this is concave function or concave extensible function. Now, can I find separation vector? I will show you, actually. So if you take, so at the origin, f and g are both 0. The possibility of alpha is only 0. Alpha should be 0. Then p 1 over 2, 1 over 2 gives a separation. So you can check. Okay. That is maximum of 0 and x1, x2 is larger than 1/2 x1, x2 minimum of x1 and x2. So this is G, this is F. Of course, this is true. Okay? So we have the separation by this vector. But actually, we are concerned with integral separation. Now, is it possible to find integral P? So you can change this to P1x, P2x2, so that this is true. But because of the symmetry, probably this would be the, or maybe 1, 0 is a possibility. But this doesn't work. So that shows that in this example, we had real separation. But it didn't imply integral separation. Okay? So this is the second lecture that we have to, second lesson that we have to learn from the examples. Okay? Now, so having shown these difficulties, now I'd like to show you theorems, which I'd like to prove here. So theorem is, there are two theorems, okay? L separation. L separation theorem says that if F is L convex, G is L concave, then we have discrete separation theorem or statement. Okay, so the convexity is not now replaced by L convexity. Then the statement is true. And also M separation, maybe you can guess already, but maybe better to write M convex and M concave, then discrete separation is true. So we have discrete separation. So I mentioned that András-Frank's discrete separation theorem. And before proving this, I will mention that here. So I stated the separation for L and M convex functions, but actually we can replace this by L natural, M natural. It's just projection of section, so it doesn't change. Okay. Although I proved the theorem for L and M today. And if you look at this, L natural convex function defined on unit hypercube, 0 and vectors. That is exactly the same as submodular set function. So you recall the definition of L natural convexity. It is basically submodularity. Okay? And we have a translation somehow. But if you translate, then we outside of the unit cube. The translation doesn't mean anything for set function. So the easy remark, but it is important remark, is if function f is defined on 0, 1 point, then f is L natural convex if and only if the set function associated with f is submodular. Okay. So using this correspondence for this theorem, what we get is Hausdorff-Frank's discrete separation theorem, which says the following. If rho is set function on E, here I assume the fully submodular defined on all the subset. That could be defined on lattice, but the mu is another set function, but this is submodular, and this is supermodular. And if they have the relation for each subset of E, then there exists some vector or modular function, say P, this is vector, such that OX is in between. Oh, but here we normalize rho at empty set and mu at the empty set is 0. This is normalization. Then we have this. And the statement is that if, so this is our separation, integer, and here is the integer separation. If all mu both integer valued, then we can take integer vector P. So this is the famous separation theorem from Hausdorff-Frank from 1982. So this statement is one of the motivations for our recognition that submodular functions are convex functions. So at that time, there are different opinions, but this is one of the statements. Actually, there are 3 important contributions, Hausdorff-Frank and Satoru Fujishige and Lottie Lovers. They all talked about convexity of submodular functions here in Bonn. Okay? So Bonn is an important place for discrete convexity in many senses. Okay, now, so I have how much time? 10:30. I think I can make it. I will try to prove this and this. Okay. So the so before starting, or actually as a preparation for the proof, let me remind you some facts from polyhedral combinatorics, the integral polyhedra. So suppose we have two integral integral polyhedra, or maybe you can assume that they are bounded, and integer vertices. All the vertices are integer vectors. Now, these properties are important. The first property is that if they intersect as polyhedron, then they contain, the intersection contains integer point. This is non-trivial. For example, if we consider this is P1 and this is P2, then P1 and P2 intersect in the middle, but they have no integral intersection. And the second property, which is stronger than that, is that if they intersect, then this is a polyhedron, then intersection is integral polyhedron. Okay, so in the formula, this means intersection and take their integer points, then take the convex hull, then you get this intersection. Okay. This is a statement. And actually, we know some classes of such a nice polyhedron. Okay. So Lemmer says that first, polymatroid intersection theorem, or base version of that. So when we translate that theorem due to Edmonds in terms of M convexity, we will get the following statement. Okay? So convex hull and M convex set. So I defined M convex set today. M convex set is a discrete set consisting of discrete points, and take the convex hull. This is integral polyhedron. It's a base polyhedron, and then it has these properties. So the family of this has property. Actually, both. B implies A. So B is stronger. Property B, and hence A. And second statement is, now you can guess. You can just replace this to L. Okay. Maybe I use color. This is M and this is L. The convex set has the same property. And the first statement was just a rephrasement, so rephrase of the well-known fact in polymatroid intersection thing. But this is also, actually, this is easier. So L convex set means that the indicator function is L convex. Indicator function of S is a set, and indicator function means it takes 0 plus infinity according to X is in S or outside. And the definition of L convex set is the associated indicator function is L convex function. And actually, this is easier object. This is known as a dual of the, so consider the shortest path problem on a graph, directed graph. And then the dual is defined by inequalities. And if the length is integral, then the dual polytope is integral. That is exactly the same as this. Okay? So this is a well-known object, but I'm using this terminology. So let's assume these two properties for set. Then from this, I'd like to derive the separation for functions. Okay. For the proof of L separation theorem. Okay. So now I have F L convex, G L concave. How do we prove? So maybe we can use convex extension and use the separation theorem from ordinary convex analysis. This is one way. That's what I will show today. Okay, so given F such that F is bigger than or equal to G at every point, then we construct convex convex extension or convex closure and concave closure. Then we hope that we have this statement. Actually, this is not true in general. We have already seen an example. But if you look at the first example, actually F is L convex or L natural convex, and G is M natural convex. So L and M are mixed. Okay, so that example is not a counterexample for this L separation theorem. So what I claim here is that if L or if F and G are both L, then this is true. This is the first statement. Okay, this is a non-trivial step. Then if this is true, then we can apply ordinary convex analysis to claim there exists alpha and P real such that if bar alpha px, so it is in between, and for all real vectors. Now, this is by convex analysis. Then we restrict x to be integers. And then on integer point, f bar and f are the same. So this implies fx and this is true for integer points. So this is the proof scheme for real separation. Okay. I want that. I have to erase it. Oh. It's a big mistake. Let's restore it. But I need this. Oh. Maybe. Sorry, Andras. I have to erase it. the generic statement again. Yeah. The discrete separation theorem said that generic form is F convex, G concave, and assumption is Fx is bigger than Gx for any at every integer point. Then the R separation claims that there exists alpha p in real such that Fx alpha plus px and g for every integer point. And this separation is that fg integer valued, there exists alpha p in integers. This was a statement. Okay. So why we have the first non-trivial step for L-convex functions? This is step for L. Why? So that we know how to construct the convex extension. So in 2 dimensions, it was something like this. Okay. For each square hypercube, we divide always in this way. Okay. And function value here, f bar of x, is a linear combination of these two, a convex combination of these three. And for a concave thing, we have the same convex combination. So x is in this real space, then it can be expressed as a convex combination of vertices. So this is x0, 1, x2. Okay? And using the same coefficient, we have fx equals a convex combination of the function at those vertices, and also g bar is given by the same formula. But by the assumption that at each integer point we have dominance. So that's why we can derive this relation from inequality at integer points. Yeah. So we are done, at least for the real part. Any questions? Oh, yes. Yeah. Good. So we have derived this extension. But now, why can we apply the discrete ordinary separation? The reason is that the Roberts show that if the given function is submodular, then this function is convex. And in the second lecture, I explained that this construction works for L-convex functions, so that this construction gives convex function. And similarly, or symmetrically, this construction gives a concave function. So these are actually convex and concave, and having this property. So that's why we can apply discrete or ordinary separation theorem in convex analysis. Okay. Good. Thank you. Okay. So here, all the components of the proofs are known result in polyhedral combinatorics. So, but this is just a combination of the idea in convex analysis and polyhedral combinatorics. Okay. Okay, so then next step is to show the integer separation. Why do we have integers p? So this story doesn't tell us anything, but we already have real vector p. And I mentioned something which is useful, property A. If we have two polyhedral, which I'm going to introduce now, the vector p is here, so the intersection is non-empty, then we can find integer p. So what are those integer polyhedra? Okay. So to prove that, so f is something like, I will see how I write, something like this, and G is something like this. But we may assume that they touch. It is the most difficult case. Okay, assume that they touch somewhere here. Let's call it X star, and this is G. Okay. So we have such a picture. We already know that they can be extended to convex functions. And vector P is a common slope or tangent here. This was P. Okay. So mathematically, we have a notation for that. So for F, we write, this is called subgradient or subdifferential. This set is subdifferential, and each member is subgradient. So the set of P's defined by this inequality. For any y. So this is a standard concept in convex analysis, but adapted to Z. And possible P here, and also for G, we have a similar definition, but the inequality is reversed because of concavity. Okay. And the possible P is in those at the intersection of the subdifferential at this touching point. Okay. If they touch, then the possible P is a subgradient of F and at the same time supergradient of G. So P should be here. Okay. But now, these are polyhedron. These are defined by many, but actually ineffectively finite inequalities. So these are polyhedron. And when F is L convex function, then the conjugacy theorem says that this is M convex set. This is conjugacy. And again, this is also M convex. And take the convex hull. Okay. So from by conjugacy theorem, we know that the subgradient, the set of subgradients, subdifferentials, is a convex hull of M convex set. Then we can apply this part, the M part of, actually the M convex set just means polymetroid, integer point of polymetroid or base polytope. So we have stronger or weaker integer property. So here we only need weaker one. So by A, there, we can find integral P there. So this is the end of the proof for integer separation for L convex functions. Okay, so maybe better to have some time for you. Just a 1-2 minutes break. Why don't you talk to each other? And you can ask each other, what was that? Then maybe you can ask me again in the afternoon. But
is step 1 going to be true for any concave and any convex?
yeah, that's what I'm going to show now. Yeah. So often in the presentation, I got a question that whether M and L can be mixed up to have our separation theorem. But already two-dimensional example shows that this is impossible. Okay.
Is there any way to go from this L separation theorem to M separation theorem?
Good question. Okay. So I have shown the proof that conjugacy theorem. If you assume that, then from L, you can easily derive M separation, and vice versa. Okay? But today I do not assume that, so I will give you separate proof. But actually, so there are 3 important theorems, and if you assume 2 of them, the other can be derived automatically. It's a good question. Yeah. Actually, that was my first proof. I first proved M separation theorem algorithmically without using polyhedral combinatorics. And I proved conjugacy next. Then I thought about the possibility of that your idea, and I could get L separation. But as you see, the L separation is actually easier to prove. Yeah. Okay, maybe I can go on. Okay. I should not erase that part. I remember. Okay, so now the proof for M separations. So again, we follow this scheme. Why the first step? No, this is not the scheme. Scheme is there. Well, we follow this scheme for the first step. So we want to find, we want to show that convex extension does not violate the dominance. So first we want to show that fx greater than gx at integer point implies that convex extension has this relation for all real points. Now I drew some picture. So this is F, and then maybe this is G. Okay. This is distance 1. There are many integer points here. Okay. So take any real vector x. So that is, for example, here. This is real vector. And how the convex extension can be defined or constructed. But actually, we don't know. In L-convex case, we know lobus extension. But here, we do not know. We know the existence. But, say, let's call this slope P. And consider this part, so B1. So I consider fx minus px. Not x is fixed. X is fixed, so y. And arg min. Let's call this B1. That means P is a slope at x. So this is a set down here. This is B1. So if we consider this slope, the minimizer is from here to here. This is polyhedron. Okay, so this is called B1. And similarly, for this slope, say Q, they have different slopes at x. Let's call this B2 is now our maximum because of concavity, gy minus qy. And as we have shown already today at the beginning, these are M-convex sets. Okay, minimizer and maximizer. So these are both M-convex set. And X is, by the choice of P and Q, X is in the intersection of convex halves. X is in the intersection. Okay? It is here and here. So let's call this P1 and let's call this P2. These are polyhedron. And then we use the lemma 1 again here. We have two convex sets, M-convex set, so we are talking about intersection. But instead of the property A, which we use stronger property B, so polymetric intersection theorem. So by lemma for M, we have property B. So that means that these are integer polyhedral. So X can be represented as a convex combination, finite convex combination, using the vertices of this. Okay? Xk is a vertex of P1 intersection P2. Now, what is good? from this, we can derive the following. What is the value of f bar x? This is linear here, okay, linear here. So it's linear in the intersection. So this can be represented as the convex combination here of the function values at vertices. Okay?
This is not unique, right?
Sorry?
This convex combination is far from unique.
Far from unique. So, but we just fix it. We just fix it. Okay? So P1, P2 looks like this. P1 and P2. And X is here. And we know that they are integers. So as you like, so you can take these 4, or if you like, you can join this. But any the possible combination, you can fix it. And then the function f is linear on P1. Then the function value at here, P bar, it can be represented as a linear combination of those values. So that's here. Okay? And also we have the same statement representation for G. So here we do not change this representation. We fixed one representation. And then G is linear in this area. So the linear extension is given by this. Okay? Then, by the assumption, we have dominance between these two. This was bigger. This is an assumption. And we have the same non-negative coefficient. So this implies that f bar x, g bar x. Okay? So x is a real vector. So we clear the first step. This is how the M separation theorem can be proved according to this scheme. So the scheme is common to L and M. But the step here really depends on the characteristic of M and L. So for step 1 there, we use Loveless extension. But we have used polymetry intersection here. So the basic logic is different. Okay? Oh, good. Finally, I can show the integral part. Okay. How can we prove the integrality? After that is the same as here. So now we go back to this picture. That is now M. This is also M concave. We have this. What is different is here. Okay. So P is taken from the intersection of self-differentials. But since F is now M convex, so this is L convex set. And this is also L convex set. So now we use a lemma for L convex set. Yes. And I didn't prove this statement, but this is just an easy exercise. If you consider dual of the shortest path polyhedra, that's just easy. So by A for L, okay, this is now L convex set. Maybe it's better to write here. Now this is L convex set. We have integer vector p. So this completes the proof of M separation theorem for the integer part. Well, that's it. Good. I could finish it.